Welcome to my channel. In continuation to our previous video, today we are discussing about Newton rings produced by transmitted system of light. Before I start the video, click on the subscription button, then enjoy the video. When I am saying Newton rings produced by the transmission phenomena, that means let us suppose the apparatus is placed over a table and we are considering the phenomena of formation of rings below the table. Suppose the apparatus means plano-convex lens over a glass plate P is over a table and our viewing microscope is below the table. Now what would be the pattern that is produced below the table? Means by the rays which are transmitted through this plano-convex lens system. Now focus on this figure. I have a plano-convex lens L placed over a glass plate P. In between space is filled with a air film whose thickness is considered to be small t. Now incident ray AB is incident on the lower curved surface of the plano-convex lens. By the lower curved surface, the ray is partially refracted and the refracted ray is BC. This BC ray is incident on the plane glass plate P. Now this ray is reflected by this plane glass plate and the reflected ray is CD. This CD ray is incident on the plane convex lens L and is reflected by the plane convex lens L as the ray DE. This ray will transmitted through the plane glass plate P and transmitted as ray number 2, orange color P. Clear? Now we consider the second ray or the second path that can be opted by the incident ray. The incident ray is AB. It is refracted by the plane convex lens. The refracted ray is BC. This BC ray is incident on the plane glass plate P. It is directly transmitted through the glass plate P and emits out as ray number 1. Clear? That means we have two rays, ray number 1 and ray number 2, green ray and the orange ray, that are transmitted out of the plano-convex lens system. Now focus on my words. I am using the word incident rays AB and by the system, complete system, not a single lens, not a single plate, by the complete system of plano-convex lens L and the glass plate P. What are the transmitted rays? Ray number 1 and ray number 2. Now I have 3 beams only. Incident ray AB and the 2 transmitted rays, ray number 1 and ray number 2. When these 2 rays 1 and 2 enter into the viewing microscope, they will have the tendency to produce an interference pattern. Why they will have the tendency to produce interference pattern? Because they have been originated from a single beam AB. Because they have been produced from a single beam AB, that means that they are coherent. And if the beams are coherent, that means they can produce the interference pattern depending upon the path difference. Now our motive is to find out what kind of interference pattern it would produce. The answer depends only on the one factor, path difference. Next, our motive is to find out the path difference between ray number 1 and ray number 2. The complete phenomena, how the rays 1 and 2 are produced, is shown on this particular slide. Now, for determination of path difference, we have considered 2 factors. Suppose small t is the thickness of air film and small r is the angle of refraction. We can find out the path difference by simply applying cosine law. What is cosine law? Path difference equal to 2 mu t cos r. Now our aim is to find out the effective path difference between the transmitted rays. For finding out effective path difference, what we are doing in the previous video? We are determining the points at which the Stokes law is applicable. So again, follow the same strategy and focus on the figure, find out the points at which the Stokes law is applicable. Here I can observe at the point C, reflection is occurring from the surface of a denser medium. Denser medium is glass plate. That means Stokes law is applicable at point number C. Clear? Second, at the point D, surface of the convex lens. Again the reflection is occurring from the surface of a denser medium. That means again I can say D is a point at which the reflection is occurring from the surface of a denser medium, meaning Stokes law is applicable. In nutshell, I have 2 points C and D at which Stokes law is applicable. That means an extra path difference of lambda by 2 would be included twice. That means the formula for the path difference is 2 mu t cos r minus lambda by 2 due to point C, again minus lambda by 2 due to point D. So the formula for the path difference comes out to be 2 mu t cos r minus lambda. Minus lambda by 2 minus lambda by 2. If you add these two terms, it would be minus lambda. Clear? Now come to the cases, special cases. What kind of incidence we are considering? Normal incidence. When I am saying normal incidence, meaning angle of refraction is 0. Cos r is 1. Clear? Because cos 0 is 1. I am considering air film, meaning refractive index of the air film is 1. Cos r 1, mu 1. What would be the formula for delta path difference? 2 into 1 into t into 1 minus lambda. That is 2t minus lambda. This is the path difference in case of transmitted system. Clear? Now our next aim is to find out the condition of central maxima, condition of maxima and condition of minima. Up to this point we have the conclusion path difference equal to 2t minus lambda. Clear? Start with the condition number 1. When I am saying central maxima, what would be the point of central maxima? Point of contact O. What would be the thickness of the air film at the point O? It's 0. T is 0. Formula for the path difference, substitute T equals to 0. That means path difference is minus lambda. Minus lambda meaning minus 1 lambda. 1 lambda meaning integral multiple of lambda. When I am saying integral multiple of lambda, that meaning bright spot is there. That means the condition of central maxima is delta is equal to minus lambda. That means it's a bright spot. Clear? Second, condition of maxima. When I am saying condition of maxima, path difference is equated with integral multiple of lambda, meaning n lambda. 2t minus lambda is equal to n lambda. That means 2t comes out to be n plus 1 lambda. This is the condition of maxima in case of transmitted system of light. Now for finding out the condition of minima, we will equate the path difference equal to odd multiple of lambda by 2. Odd multiple 2n minus 1 lambda by 2. When I equate the path difference with this, the condition comes out to be 2t is equal to 2n plus 1 lambda by 2. This is the condition of minima. Now we have determined the condition of maxima, condition of minima in terms of 2t. Follow the same procedure as we have done in case of reflected system of light. My motive is to find out the diameter of the bright ring, diameter of the dark ring. For finding out the diameter, what I have done there, I have determined the expression of 2t in terms of diameter. Again, I am saying the same strategy is adopted. I have determined 2t in terms of diameter dn. Consider a plano-convex lens whose radius of curvature is r. Radius of curvature is the radius of a sphere of which the lens is a part. So, I have imagined a sphere whose radius of curvature is capital R. That means here CF is capital R, radius of curvature, CO is capital R, radius of curvature. Because the green color lens is placed over the yellow color glass plate, that means in between we have the air film. The air film thickness is indicated by small t. That means the parameter FQ is small t. Because the FQ is parallel to EO, EO is also small t. That means the parameter CE is equal to R, radius of curvature, minus small t. Now focus on the right angle triangle CEF. In this right angle triangle, CE is R minus t, CF is capital R, radius of curvature, and what is EF? Radius of the air film. Because the radius of air film is equal to the radius of nth fringe, it is indicated by Rn, small rn. Now apply the Pythagoras theorem in this right angle triangle. Hypotenuse square, meaning CF square, is equal to CE square, perpendicular square, plus base square, EF square. Clear? Hypotenuse is R square equals to R minus T square plus small rn square. Open the square, then cancel the common term from the both side. R square would cancel out. T square very small because the thickness of air film is very small. Its square would be very small, may be neglected. Expression comes out to be Rn square is equal to 2RT. That means 2T is equal to Rn square by capital R. Rn radius may be expressed in terms of diameter as dn by 2. That means expression comes out to be dn square by 4r is equal to 2t. Label it as equation number 3. This is the expression of 2t in terms of dn square. Now equate the condition of minima and equate the condition of maxima with the expression 2t is equal to dn square by 4r. For finding out the diameter of the nth bright ring, we will equate the condition of maxima with dn square by 4r. Equate equation number 1a with 3. dn comes out to be under root of 4n lambda r. Clear? Diameter of the nth dark ring, meaning equate the condition of minima with dn square by 4r, and the value of dn comes out to be as shown here. So up to now we have determined the expression for part difference, condition of maxima, condition of minima, diameter of nth bright ring, diameter of nth dark ring in the transmitted system of light. So what kind of fringes are obtained? Concentric circles, bright and dark circles with central spot as bright spot. So the result is central spot is a bright spot with alternate bright and dark rings. So this was the topic of Newton rings produced in case of transmitted system of light. The only difference between the Newton rings produced by the reflected system of light and by transmitted system of light is, in case of reflected system of light, the central spot was dark. In case of transmitted system of light, the central spot is bright. Clear? So this was Newton rings produced by transmitted system of light. So in continuation to this, we will discuss the applications of Newton ring experiment. So let's start with the topic. First application is wavelength of light. My aim is to find out the wavelength of light using Newton ring experiment. Clear? First I will determine the theoretical formula for lambda. What was the formula for the diameter of nth dark ring? Formula was dn equals to under root of 4n lambda r by mu. In that case, we have written mu equals to 1 because we have particularly considered the case of air film. So for air, mu was 1. Now we are considering a general case, that's why we have written in the denominator mu as a symbol, not substituted the value of mu equal to 1. So the formula is dn is equal to under root 4n lambda r by mu. Clear? Next, what would be the diameter of n plus mth dark ring? In the formula of dn, replace n by n plus m. So the value comes out to be under root of 4 into n plus m lambda r by mu. Now, if I find out dn plus m square minus dn square, common term would cancel. Common term is 4n lambda r. It would cancel and remainder is dn plus m square minus dn square is equal to 4m lambda r. If from the right hand side I keep lambda on right hand side and bring all other terms on the left hand side, so what would be the formula? Lambda is equal to dn plus m square minus dn square over 4mr into mu. Is it clear? Now if I consider the case of air film, again mu would be 1 and the formula comes out to be as shown here. This is a theoretical formula for determining lambda. Now focus on this formula and determine the factors upon this lambda depends upon. One is dn plus m square minus dn square, meaning the difference in the squares of diameter of nth ring and n plus mth ring, divided by m. M meaning how many rings we have taken, the gap of how many rings we have taken. Capital R, radius of curvature of plano-convex lens. If we determine the values of all these parameters and we substitute the value in this theoretical formula, we can find out lambda. Clear? So on the next slide, we will show experimentally we are finding out the values of all these parameters, and by substituting in this formula we can find out the experimental value of lambda. Clear? Now set the experiment to find out the value of lambda using Newton rings experiment. First we focus on the Newton rings by reflected system of light. Here the central spot is dark. Now connect an instrument named as micrometer with a viewing microscope. This instrument is used to note down the position of nth dark ring and to note down the position of n plus mth dark ring. Clear? Now when we have set the Newton rings in the viewing microscope, we will set the crosswire of the viewing microscope on left hand side, third dark ring. Note the reading using micrometer. Now move the microscope and bring the crosswire of the microscope on the right hand side, third dark ring. Note down the position. Suppose this position is B and the previous position was A. Now, if we find out the difference B minus A, this would be the diameter of third dark ring. I may designate it as D3. Similarly, we can find out D6, D9, D12. In the third column, find out the squares of these diameter, D3 square, D6 square, D9 square, D12 square. In the fourth column, find out the difference between these, D6 square minus D3 square. We have taken the difference of 3 rings, diameter of third, diameter of sixth. Then D9 square minus D6 square, again the difference of 3. Then D12 square minus D9 square, again the difference of 3. That means how many fringes gap we have taken? M is 3. Now from the fourth column, I may take the mean of these values. That mean is Dn plus M square minus Dn square, mean value of this, and M is 3. So experimentally, I have determined the value of M, value of Dn plus M square minus Dn square. R, radius of curvature of plano-convex lens, will be given by the manufacturer by substituting the values of all these parameters in the theoretical formula of lambda. As we have shown on the previous slide, we may determine the value of lambda experimentally. Clear? So this was the method to find out the value of wavelength of light using Newton ring experiment. Next application of the Newton ring experiment is find out the refractive index of liquid film. For this, the setup required is plano-convex lens, liquid film, and last is glass plate. That means now we have the Newton ring experiment, Newton ring setup, and instead of air film, we have taken the liquid film now. And our aim is to find out the refractive index of that liquid film. We will discuss this topic in 2 different categories. First method, when lambda is known to us, and in the second method, we will find out mu when lambda is unknown. So let's consider the method number 1. When lambda is known to us. When I am saying lambda is known, I apply the formula for the diameter of nth dark ring. Dn square from formula is 4n lambda divided by mu. Same pattern, find out Dn plus m square. It comes out to be 4 into n plus m lambda by mu. Find out the difference. And from here, keep mu on one side and bring all the terms on the other side. So we will find out the theoretical formula for mu. Again observe this theoretical formula. The same parameters are required as we require in case of lambda. What are the parameters? 4 constant, m gap of rings, lambda known to us, radius of curvature known to us. In the denominator we have dn plus m square minus dn square. We may experimentally determine this factor as we have discussed on the previous slide. By experimentally determining the values of all these parameters and substituting in this theoretical formula, we can find out the value of refractive index of a liquid film. Clear? Case number 2, when lambda is unknown. In this case, I would perform the experiment in 2 steps. Step number 1, find out the diameter of nth dark ring with air film in between. Formula would be dn air square is equal to 4n lambda divided by mu. Mu in case of air is 1. Label this equation as equation number 1. Second step, perform the same experiment with liquid film in between. Dn square in case of liquid is 4n lambda divided by mu liquid. Label it as equation number 2. Divide the two equations and we can find out the theoretical formula for mu liquid as dn square air divided by dn square liquid. Now experimentally I can find out the diameter of nth ring with air film. Yes, the diameter of nth ring with liquid film. By substituting these experimental values in this theoretical formula, I can find out the refractive index of liquid. When lambda is unknown to us, because lambda is not used in this equation. Thus, we have determined the refractive index without knowing the value of lambda. Last is, we can find out the thickness of a thin film trapped between two curved surfaces. This may be considered as a kind of conceptual question. Suppose we have two curved surfaces. Green one is one curved surface and the red one is another curved surface. We have air film trapped between these two curved surfaces. Suppose the thickness of that air film is small t. In my figure, I have shown this thickness or this air film by blue color. Now, our aim is to find out the thickness of this air film. I simply use the previous formulas and find out the value of this thickness T. Clear? So now come to the point. Suppose, imagine we have only one curved surface. We are considering the curved surface green one, whose radius of curvature I have taken as R1. The complete parameters are shown in green color. Now, this plano-convex lens system is placed over a glass plate P. So, what is the thickness of thin film trapped between surface green one and the glass plate yellow one? Thickness of air film is Pt. Now apply the formula. Thickness of film is T is equal to Rn square by 2R. That means Pt is Rn square by 2R1, because in case of green surface the radius of curvature is R1. Clear? So Pt meaning thickness of air film for the green curved surface is this one. Now next is red curved surface. What is the thickness of film trapped between red curved surface and the glass plate P? Observe the figure, it is Qt. So what is the radius of curvature of red surface? R2, capital R2. So what would be the formula of Qt? Rn square divided by 2R2. My aim is to find out small t. If I observe the figure, small t is equal to Pt minus Qt. Substitute the value of Pt and substitute the value of Qt. Take the term common, Rn square by 2. Within the bracket, we have 1 by R1 minus 1 by R2. So this is the formula for the thickness of air film trapped between two curved surfaces. Clear? On the same pattern, we may have the case curved surface shown by the green color, curved surface shown by the red color, and our aim is to find out the thickness of air film trapped between these two curved surfaces. Here we have shown the glass plate by the black dotted line. Now, what is the thickness of air film trapped between green surface and the glass plate P? That is shown by black dotted line. It's PQ. Radius of curvature of green surface is R1. So formula PQ is equal to Rn square by 2R1. Clear? This is the thickness of film trapped between green surface and the glass plate. Now consider the red surface. What is the thickness of film enclosed between this red surface and the dotted line? Qt. Apply the formula for T. Qt is equal to Rn square by 2R2. because radius of curvature of red surface is R2. So what is the total thickness of air film trapped between red and green surface? Small t equals to PQ plus QT. Add these two factors. Take Rn square by 2 as common. Within the bracket we have 1 by R1 plus 1 by R2. So this is the formula for finding out thickness of air film trapped between two curved surfaces. These are the applications of Newton ring experiment. Done? Thanks. This was the complete topic of Newton rings. For more updates of upcoming videos, click the subscribe button. Thank you so much.